Assalamu alaikum all. Today, inshallah, we are going to talk about the classification. Basically, we're going to complete the CAD system, the first complete CAD system for ECG arrhythmia classification. And before we do that, we have to consider the performance matrix of biomedical diagnostic systems so that we can basically know the difference between the different models that we're going to use for classification. Okay, so basically, let me share the screen. So basically, whenever you're trying to diagnose a patient, you usually have two outcomes. Usually, you either have it as a positive or negative. Okay, so basically, if you look at what you have there in this figure, basically this is the examination. This is the examination outcome. Okay, either it's positive or negative. The point is, you really don't know at this point when you do the examination, you don't really know the truth. But if you know the truth, then you have basically this is the truth. It can be either positive or negative. So basically, if you examine the patient and say that the patient is positive while he is positive, then this is true positive. If you examine the patient and say that the patient is negative while he is actually negative, then this is true negative. We have two false states here. One of them, when you diagnose the patient as positive while he is negative. And that's why we call it false positive. Okay, false positive means that you diagnose the patient as positive while he was negative, in fact. The other way around, you have either basically you diagnose him as negative while he was positive. That's why we call it false negative. The importance of putting the results like this, basically this notation actually is called the confusion matrix. This is actually one of the very important notations that people use in biomedical diagnostics. It's very important because basically you separated or you basically make distinction between the false negatives and the false positives. So basically both of these are errors. This is error and this is error. Okay, both of them are errors, but actually one of them is much more dangerous or much more hazardous to the patient than the other. Which one is more hazardous? If you diagnose, if you have false positive or a false negative, which one of these would be more dangerous to the patient? Can you please answer?
Positive.
False positive? You talk about false positive?
Yeah.
Actually, no. The problem is when the patient is positive and you diagnose him as negative, this is the most dangerous. When the patient goes to the hospital and basically the hospital tells him that you are okay, you don't have any problems, and you go on and basically the patient goes on and basically stays for another year or something like that while he actually has a problem. And after this year, it will be a big problem. Okay, so basically the false negative is more dangerous. This is actually much more dangerous than this. Okay, false negative is really dangerous. False negative, you told the patient that he doesn't have any problem while he has a problem. If the patient has a heart condition and you basically told him that you don't have any problem, your heart is fine, and basically he goes on and basically plays sports or basically keep jogging or playing soccer or something like that, basically it's going to be a problem for him because basically the condition, the heart condition might actually cause a much bigger problem if you don't diagnose it early. So this is actually false negative is much more dangerous than false positive. For the false positive, you told the patient that you have this heart condition. The patient is upset and basically thinks that he's going to die and things of that sort, but he will actually have to do some further testing. Okay, And basically, when he does some further testing, he will find out that he's not positive. So basically, it caused the patient some anxiety. It caused him some stress for him and for his family. But at the end, there was no actual risk to the patient. For the false negative, it's the other way around. You basically told the patient that you are fine, but actually he wasn't. So basically, this distinction is extremely important. Okay? If you consider something like the accuracy basically, if you're trying to basically, if these are my results, basically, if I have patients and basically the results came out like this, I had 100 true positives, maybe 200 true negative. I have here maybe 20. I have here maybe like 10. Okay. If you want to compute the accuracy, how can you compute the accuracy from these results? What is the accuracy? Is equal to what? The correct diagnosis as a percentage of all, right? This is the accuracy. How many are accurate? How many are correct? Basically, TP, true positive, plus true negative, over all of them, true positive, true negative, false positive, false negative. The problem with the accuracy is that basically you don't make any distinction between these two. So for example, if all the error was here, it doesn't matter at all for, when you look at the accuracy. The accuracy looks at the incorrect ones. But actually, this is a big problem for the accuracy. That's why for biomedical diagnostics, we need some further measures or other metrics, other ways of expressing the performance of the system to be able to make distinction between these two types of error. Okay? So now we're going to consider a few new performance metrics that might actually resolve this problem, or basically give us a way of looking at this. Okay, so in order to do that, basically this is the same matrix. This is exactly the same matrix. Matrix that you looked at is basically right there. Okay, I can, sorry. Yeah. This is the matrix right there. This is exactly the same one. Okay, this is exactly the same. But actually, in order for you to be able to realize the meaning of what we're going to talk about, basically we have to consider that the positive is affected by disease. The negative is not affected by disease. Okay, so basically, if you consider this is the truth, the summation of the true positive and the false negative is basically the count of cases or count of patients that actually are positive. Okay, so basically when I talk about all affected, this is basically the count of patients with the disease. On the other hand, if you sum these two, this is the true negative. They are definitely negative. They are not affected. The false positive are negatives that you diagnose as positive, but they are still negative. They are in fact negative. So basically the summation of these two is all non-affected. Here for the examination, if you sum these two, basically you are going to give all the positives that you have in your examination. So basically, if you look at basically the outcome of the examination, if you sum these two together, you're going to get basically all the positive diagnoses that you gave to the patients. How many positive diagnoses you gave to the patients. If you sum these two, basically they will be all negatives that you gave to the patients. Okay, the grand total of all of them, the number of cases, is basically the summation of all these numbers. What are the metrics that we can use to basically distinguish between the different types of error? The first one, basically I should probably have this visible. Basically the first one is called sensitivity, or what's called true positive rate. Okay, it's the ability to identify the presence of disease. Just look at this column right there. These are all the patients with the disease. Basically, I was able to detect only these. The other ones I was not able to detect. So if I divide true positive over true positive plus false positive, or the total number of affected, this will give me the sensitivity and will give me the ability to identify the presence of disease. For example, if I said that the sensitivity is 90%, this means that if I have 100 patients with the disease, I will definitely be able to detect the disease in 90 patients out of 100. Okay, so this is very important. Okay, the other way around, the specificity is basically the ability to identify the absence of disease, which basically we're talking about this column right there. Okay, so basically this is a sensitivity, this is a specificity. If you look at this column here, we were able to detect the negatives correctly here, but actually the total was a little bit more. So basically, if you divide Tn by Tn plus false positive, FP, or non-affected, you're going to get basically the total number of the percentage of patients that without the disease that you were able to detect them. Here, for example, if you have 10 patients positive, okay, you will be able to detect 9. If this is, for example, was like 80%, then if you have 10 patients, 10 negative patients, this means that you will be able to detect 8 of them, basically say that 8 of them don't have the disease correctly. Okay, so if you look at these, actually, these make distinction between these two types of error. Basically, if you're considering that this is very important, if the false negatives are really important, then you have to have this number as close to 100 as possible. Because basically the error here will be basically the error rate for the false negatives. Okay, so basically it's very important to have the sensitivity higher than the specificity, because the error here is more dangerous than the error here. Okay, but it shouldn't be anything like, for example, sometimes you can have it like 100% here and 0% here. This doesn't make sense. Basically, if I have a classification system that basically, if you have any patients, would give you all the time positive, without having, this is a black box, and basically this is the patient, okay, gives you all the time positive all the time. If you have a system like this, then any patient here, if you have positives, they will definitely be identified as positive. Okay, so basically the sensitivity will be 100%. But how about the specificity? Actually, all the non-affected cases will be also diagnosed as positive. So basically, the true negatives will be 0. So basically, the specificity will be 0%. This is not acceptable. If you have a system that looks like this, this is not acceptable. You have to have the sensitivity and specificity almost of the same order. Other than that, it doesn't make sense. Then you don't have to go to the doctor then. If you want to have a sensitivity 100%, then you just classify everybody as having the disease. That's it. You don't have to go to the doctor at all. We don't need a diagnostic system if you have a system like this. Okay, so both are important. Okay, you have to have these both numbers as high as possible. They are not very far from each other, but actually it's acceptable to be like this. For example, 90%, 80% is okay, but you don't really want to have 50% and 90%. This is not good. You want to have the sensitivity normally higher than the specificity. Okay, but if they are both high, if one of them is like 98%, and the other one is if the sensitivity is 98% and the specificity 99%, this is okay, because actually this is high enough. Okay? But you don't want to have the specificity much higher than the sensitivity. So this is one of the measures that you are going to use. Basically, whenever we do classification, we're going to estimate the confusion matrix and just compute these measures. another measure or another couple of measures which are called basically positive predictive value and the negative predictive value. In both of the upper two metrics, they basically give you information, what they call it, pre-test information, meaning that you use the sensitivity and specificity to basically compare different systems before you actually do the test. So, for example, I can compare the sensitivity and specificity of MRI versus ultrasound in detecting, for example, breast cancer. Okay, this is actually the sensitivity and specificity will give me the numbers to make me able to choose which one of these should be the better way of doing this diagnostic test. The positive predictive value and the negative predictive value look the other way around. Okay, so the first two are basically pre-test. The other two are post-tests, meaning that if I get a good result, if I get a positive result, how reliable is that positive result? Okay, then I'm looking at, instead of looking at the columns here, I'm looking at the rows here. Okay, basically, just consider the positive diagnosis here. You have true positives and false positives. So if I divide the true positives by the false positives, possibly, or the total here, all the positives, I can get an estimate of how reliable my diagnosis is. For example, if I have, as I was saying, maybe I can just use the same numbers that we used before. Basically, we had 100 true positives here and 20 false positives. If I divide 100 over 120, this will give me how reliable my positive diagnosis is, or how often the positive diagnosis was actually, in truth, it was positive. Of course, it would be ideal to have it as 100%. Actually, here it's not going to be 100%. It's going to be 100 over 120, meaning that it's going to be a little bit less, almost 82% or something like that. Okay, this means that when you get a positive diagnosis, there is a chance of 82% that this is actually positive. This is very important because if you have a diagnostic test that will give you a positive value of 50%, then it's just a toss. Basically, just a flip of a coin. Basically, it's 50-50. It doesn't make sense, actually. You have to actually do another test in order for you to be able to basically make sure that the positive is actually positive. If the positive predictive value is almost like 95%, something like that, then it's very likely that actually when you get a positive rate, when you get a positive diagnosis, that it's actually positive. Same thing in the negative. Negative predictive value, you look at the other row here, you basically have the true negatives over the total negative. If you get a true negative or basically negative predictive value of 95%, then if you do this test, if you do this diagnostic test or the diagnostic examination and get a negative diagnosis, it's very likely that it's actually negative, which is good. Okay, so basically these four different measures are really important because they look at different things and they give you insight into which test to use and how reliable the result from the test after you do the test. So whenever you're trying to compare different kinds of diagnostic systems, which is basically what we are going to do, basically the classification we're going to do today actually will basically construct a diagnostic system. And whatever we get out of this diagnostic system, we would like to examine from the point of view of sensitivity, specificity, the positive predictive value, negative predictive value, and so on. And as you can see, basically, whenever you have the confusion matrix, TP, FP, FN, TN, the four numbers in the confusion matrix, all the numbers here, all these measures basically can be computed with these four numbers, and that's it. The accuracy, as we said before, is the true over the true diagnosis, which is true positive plus true negative, over the total number of cases. So basically what we're going to do today is just compute the confusion matrix, and basically based on confusion matrix, you can just list or compute these very simple measures that are really important. You're never going to find any diagnostic or any computer-aided diagnosis system or any arrhythmia classification system that doesn't use these kinds of performance metrics in order to report the results. Because basically, if you report the results this way, then you completely specified the performance of your system, which is important basically in such systems. Extremely important. You have any questions about the performance metrics? Any questions? Okay. So once we compute these, one of the things that you can use actually what's called receiver operating characteristics. Basically, it's a curve that draws the sensitivity with 1 minus specificity. Okay. Sometimes people call this true positive rate. Sensitivity is actually the true positive rate. The specificity is 1 minus the specificity itself is the true negative rate. Okay, so if you draw these, usually for any classifier, there are parameters that you can change. For example, if I say that if I have a system that, like what we talked about before, looks like this, whatever, okay. You have circles and axes, okay, something like that, for example, okay. I can actually classify the axes from the O's, from the circles, basically, by just putting a threshold. I can put the threshold here, I can put it here, I can put it here, I can put it in different places, okay. Basically, the ROC curve basically draws the sensitivity versus 1 minus specificity for different values or for different parameters here. Like for this is like number 1, this is probably number 2, number 3, and so on. You basically use different parameters and basically draw a curve basically from these values, basically, okay? As you see here, if you have something that looks like this point right there is basically you have sensitivity of 100% and specificity of what? 100%, right? Is that correct? Is that correct? Actually, it's supposed to be here 100%, but actually the specificity here, since this is 100%, specificity will be 0, which is a trivial system that we just talked about. Okay, so this point right there doesn't make sense. This point right there is the opposite. You have a sensitivity of 0 and specificity of 1. Doesn't make sense. So these points don't make sense. The points in the middle actually are the points that make sense. And you can trade off sensitivity versus specificity, but you would like to have something, this point, for example, this is a good point because here you have the specificity will be like this, 1 minus this value. So basically, 1 minus specificity means that the specificity is this much right there. Okay? The sensitivity will be here. So basically, both of them are kind of high and kind of close. This is a good point. But in these curves, usually if you have a good classifier, usually you end up having a curve that is actually very close to filling out this box right there. If you have a poor classification, basically the line will be basically just a diagonal right there. So the minimum of the area under ROC curve is 50%, because it's basically half or 0.5, because it's half this box. The more you have here, the more the ROC curve becomes close to this point. This point is the ideal point. If you got to this point, you are 100% sensitivity, 100% specificity. Basically, this sensitivity is 100%. And 1 minus specificity is 0, means that the specificity is 100%. So this point is ideal. But basically, the closer you get to there, so basically this point here is better than this point, than this point, this is the worst. So the closer you get to there, the better the classifier will be. So basically the area under curve is one of the measures of the performance of the classification system. Okay, so basically we're going to measure all these things whenever we're going to implement now classification systems. We're going to use these measures in order for us to be able to compare the different systems. Okay, so we're going to basically compute the sensitivity, the specificity. First of all, we're going to compute the confusion matrix. From the confusion matrix, we're going to compute the sensitivity, specificity, false positive rate, false positive and false negative, positive predictive value and negative predictive value, and the accuracy. And then we're going to compute the area under curve. Okay, which is a good measure for basically the higher the area under curve, the closer you are to the ideal point where you have 100% sensitivity and 100% specificity. Okay, is that clear? Please stop me if you have any questions anytime, okay?
It's okay, Doctor.
Okay, so right now we're going to go back to our code. This is a code that we had last time. Maybe I can just run it again. This is exactly the code where we computed the features and basically looked at them and did the feature selection and basically selected 34 out of 39, basically, okay? So basically we did the t-testing and basically removed 5 because they had a p-value that was high. For example, this one here was higher than 0.05. This one here was definitely high, and so on. This one definitely okay, but definitely not less than 0.05. So basically we did that last time. What we need to do now is do classification. Just try the classification. What do we need to get started with classification? Okay. Okay, we have basically 2 phases in the classifier operation. Basically, we have the training phase. We have to have basically a vector. Basically, this dimension here is the number of cases, or the cases, basically. Each row is a case. And this right there is the features. So basically here now, if you remember from last time, we have the feature A, feature N. Here actually it's opposite, it's just 34 features times 64 cases. Here 34 features times 64 cases, okay? So we need to transpose that. We need to have it as 64 times 34. So basically what we have now, what we have in our system right now, we have basically that's fine. We have, for the normals, we have 64 cases. For the abnormal, we have 64 cases. So I need to have both of them in this vector right there. So basically, I'm going to have 128 cases, and we have 34 features for each. So basically, this is basically what we usually call as X. This is the input. This is the measurements, okay? Okay, this is the X, the X vector. Okay, we need another vector that is very important, which is actually basically this dimension here is exactly as the dimension here, and the other dimension here is 1. Okay, we call this vector Y. Okay, this is basically the observations. Not the observations, this is the labels. Sometimes people actually call this the observations. And this is actually the labels. For example, if I have here a case, the first case, it has to have a certain diagnosis, okay? So maybe we can just put them at numerical value. We can just say that 1 is normal, or 2 is abnormal. Okay, or we can say 0 and 1, we can say -1 and 1, whatever, it's up to you, but just put two different numbers. Okay, just choose whatever you want. So if we take these vectors n and a and put them together, concatenate them, basically, we have to have, for the normal cases, we can basically put it as 1, and for the abnormal cases, we put them as 2. Both x and y, this is the y curve, basically, or the y vector, basically, is the labels. I need both x and y to train the classifier, to be able to train the classifier. Sometimes, actually, I can give that classifier, that's fine. For the training phase, at least we need the x and y. So let's now go and do that. What we need to have now is, basically, I need to take feet A and feet N and just put them in one vector of dimension 128 by 34. So first of all, I have to transpose each one of them and then concatenate them using semicolon. Let's try that. So now I ended, maybe I can just save that. This was the lecture 8 code. I'm just gonna call now that as lecture 10, okay? And just let's just call it feature 1 still, okay? So now we'll prepare data for classification. Okay, so let's call the first one as X, capital X, or maybe you can just call it X train. Is going to be basically feet N transpose and feet A transpose, but actually we have to concatenate them, along the first dimension. So we have to put semicolon so that they concatenate in the first dimension. Let's see what that would give us. If I do that here, let's see, X train now is 128 times 34. This is exactly what I want. This vector has 64 normal cases and followed by 64 abnormal cases. So I need now to have another vector, let's call it Y train. Y train. I need to have, would you like to have the normal as 0 or as 1? It's up to you.
1.
Okay, let's take it as 1. So basically, it's going to be 1 of, we know that the first vector, we have 64 abnormal, 64 normal cases. And how about the other one, the abnormal? What would you like to have the abnormal case, the label for the abnormal case? We have 1 now for the normal. What should we do for the abnormal? Just take it as 2? Let's take it as 2. 2 times. Actually, it's up to you. It doesn't matter. It has no effect at all. Just choose 2 different numbers. 2 times 1 of 64 and 1. Okay. So now after we run that, we're going to have X train 128 times 34. Y train is going to be 128 times 1. We need to classify now. We have the X train and Y train. We need to classify them. Actually, if you want to do that, you probably want to do the, basically you have to have the data from the testing as well. Okay, you have to do exactly, basically just take the data. Basically, you have to have what we did here, basically, we took the data, the original data, or the original signal space. We converted that to what's called the feature space. Meaning that here we had 128 cases. Each one of them has 1080 points. I converted that to a feature space that has 128 cases times 34 features. The more you reduce the features, or the number right there, the number of features, the smaller the number of features actually, and the more useful, the more representative features you use, the better the classification will be. Okay, so basically you did that for the training data. Okay, if you want to test, if you want to have a different testing data, for example, if I train the classifier with the data that I have before, that 128 cases, I have here 64 cases, which is basically 32 normal and 32 abnormal. Okay, basically I need to do exactly the same thing. I need to move the data from here to here also. So I need to compute the features for my testing data as well. So I have to do that. Okay. Before we do that, let's look at the classifiers that we have. How we're going to classify in MATLAB. Basically, if you want to do that, basically just go here and go to the documentation and just write classification. Let's start with something like k nearest neighbor is right there, or let's just see the classification in general. Classification. There are so many different classification techniques: classification trees, discriminant analysis, naive Bayes, nearest neighbors. Nearest neighbors is basically the one that we want. It's a k nearest neighbor. Let's look at that. Basically, you're going to have different functions. Create a model. Usually for MATLAB, you create a model and use this model to classify. So here you have a function called fit e KNN, and you basically follow it by classification or observation using predict. Basically, let me show you some code here so that you can realize how this is done. Basically, you have a model. You have just say model is equal to fit c KNN. You put your observations x and your labels y. You can have also some parameters like the number of neighbors. For example, for KNN, this is k. This is k equals to 3. If you want to have k equals to 1, you put it here as 1. If you want to have it here as 5, you change it here as 5. You have here several other parameters that you can optimize. Here you have the optimization method, you have the distance measure, you have the standardization of data. You have several things to basically optimize. If you don't want to optimize anything, you just use the defaults. Just say fit c KNN of x and y. That's it. Okay. So how about if you want to classify and see what, just see your data. So see the classification, how the classification of your data based on this model. Basically, like this one here, maybe it's still available here also. I don't see it. But the thing is, you have a model that comes out of this function. The predict basically takes this model and your x for the testing data, the observations for the testing data, and gives you the labels, the estimated labels for the testing data. So basically, using 2 steps, you can do k nearest neighbor classification. Very simple. Just fit c KNN, just create the model and then predict. That's it. The point is, we have so many different classifiers. These are not classifiers. These are families of classifiers. Okay, so basically each one of these has several techniques, and each one has parameters, and you need to classify or need to optimize all of them. This is actually a time-consuming task. What I'm going to show you now is an application that became available in MATLAB, and this is why actually we needed a recent version of MATLAB. Basically, you go to apps, there's something called Classification Learner. Classification Learner. If I open it, this is an application that allows you to basically try all classifiers, okay? And basically try, whenever you try the classifiers on your data, you can come up with the one that has the best results and basically get the model out of it right away without having to do that manually. Okay, let's try to do that. First of all, you can use parallel, basically, if you want to do that, but actually let's start a session first. Basically, you can start a session from the workspace. Now we have X train and Y train. The data is now in the workspace. So we can do that. We can just start a classification learner app from, get the variables from the workspace. It asks you for your data, for X data first. Okay, this is the data set variable, this is the X, and the response is the Y. So basically here, I just come here and choose X train. Okay, and the response here, actually, if you don't say, if you don't have, you can just use the data set, the same variable here, and put in the last column, you put the label of the data. But actually, it's easier or more convenient to have it like this. Just have the response from the workspace. Once you put here X train, it will assume that the other one is just Y train and give it to you right away. So now you chose X train and Y train as your data. You have something here called validation. I'm going to basically start with no validation first and basically show you how it works and then show you how or why we need something called validation. Okay? So once you do that, you already chose your data as X train and Y train. Okay. And I'm going to say start session. Usually, if you have a problem like this, it usually likes to use a parallel. Basically, you can use parallel, basically parallel compute. If you have a multi-core processor, basically it usually starts the parallel pool so that it can actually do the calculations a little bit fast. Anyway, right now we can actually do something called feature selection. This is not the feature selection that we did. Basically here you just choose which ones of the feature you want to include and which you don't want to include, okay? But actually we already did the feature selection, so basically we're just going to keep all of them, okay, for now at least. Here you choose the model that you have. Basically, remember that we have, I was telling you that we have different families. These are the families of classifiers. See here, decision trees, discriminant analysis. Each one has several variants. And some of them actually have parameters that you can optimize. So we have here decision trees, discriminant analysis, logistic regression, naive Bayes, support vector machines, nearest neighbor classifier, the KNN, ensemble classifiers. So basically you can choose all of them if you want to. But basically there is one convenient feature, which is basically just use what's called all quick to compute. Okay, basically this trains the fastest classifier so that you know I get a round figure of what you have. Okay, so let's choose that all quick. Okay. And basically, whenever you choose that, you just start train. Okay, just say train here. What's going to happen is that this, okay, it's still starting the parallel pool. But the first time you do that, it's just going to take a few seconds just to start the parallel pool so that it can compute on the parallel processing to compute your results. So basically, just do that once at the beginning, and basically later on, it's not going to use it again. If you use it again, it's not going to basically do anything. So basically now it's going to start. See here, you have several of these, and start computing and all of them. You have one that gave you 100%. 100%. Let's look at that. Basically, you can come here and click that, and you have here the details of basically whatever you have. Here, for example, the model type is basically what's called preset fine KNN, number of neighbors equal to 1. So basically, you didn't have to try several values and choose which one is better. You have Euclidean distance. This is a distance measure that was used in measuring the distance or the neighborhood that you have. Basically, if you remember from last time, we said that in the nearest neighbor or k-nearest neighbor, we sort for a test case, we sort the distances from this test case to all the cases in the normal and abnormal, and see which ones are closest. and then do voting in order for us to be able to classify this case or this test case to the closest set of points from the data, from the training data. And the distance weight is equal. Standardization of data is true. I'm going to explain these terminologies, but actually we got results right there. If you want to see the confusion matrix, it's right there. This is the confusion matrix. You just click here. It's going to open a tab here with the confusion matrix. This is the confusion matrix right there. Okay, you have since it's 100%, then it's 64 true positive and 64 true negative. Actually, it's the other way around because true was the positive basically. So the positive is here. So it's just be sure that just to don't get confused by that. Okay, and basically you can see also the ROC curve. It's definitely correct, but see here, because it's 100%, you actually, the curve is basically touching the ideal point, right? This is the ideal point here, okay? And the area under curve is 1, okay? So basically, as you see here, you got all the basic from the confusion matrix. You can compute all the values, all the metrics that we talked about, and from the ROC curve, it's already 1. Let's compare that to one that didn't perform that well. This is another KNN, but it's a different type. See, the ROC curve is a little bit, it's not touching there. Okay, so basically the ROC, the area under curve here is 0.94. It's not 1. So it's worse than the one that had 100%. Let's look at the confusion matrix. Whenever you are clicking here, if this one is highlighted, all the values here, all the figures here will be basically for this one right there. Okay, so this is 64, this is 20, this is not good because actually 2 is the abnormal cases. So 20 is not very good. Okay, so 20 out of 64, this is really bad. So basically, you're going to have a very low sensitivity because of that. Okay, so basically, in this particular case, if you want to compute the specificity, it's going to be like 100%. The sensitivity will be 20 over 64, which is going to be almost 30%. It's really poor. Okay, and basically, the ROC curve is definitely there. The problem is basically what we have is just, we use no validation. The problem is when you do that, just explain the terminology. Basically, you have a data set of 128 cases, okay? In order for you to get measures, performance measures, you have to divide into training and testing. Without validation, you do that once. So basically, I divide the training into, for example, out of these like 90 cases, and the other ones will be like 38 cases, for example, okay? And that's it, once. I just train using these and test using these. The problem with that is sometimes you get the training cases or the testing cases might be close to what you have in the training cases. Sometimes you get combinations of training and testing that will give you performance that is much higher than what is actually obtainable. So what people do actually in order for you to be able to do that is basically do something called multifold cross-validation. Okay, this is actually what we did here. Basically, if we do that once, you call it just no validation. Okay, here if you do multifold cross-validation, then you keep the division as 90 and 38, but actually you repeat that 5 times or multiple times. With random distribution. meaning that randomization of cases. Okay. So basically, you choose 90 random cases each time, and the remaining would be also random cases for the the training and testing. Okay, each time you choose different 90 and different 38, and at the end you average all of them. Each one of these is called a fold. You repeat that, another fold, fold 1, fold 2, and so on, fold M, for example, and you basically add them together and just average the performance. This will ensure that basically you don't have a preferred or basically an estimate of the performance that is much higher than the actual one. This ensures that you will have a robust result. Let's try that. Here, actually, you can try that now because you already choose, when we open the session, we chose basically that we don't have any validation. We're not going to apply any validation. So basically, I'm going to try another one. So basically, I'm going to use a new session. Whenever you have a new session, you basically close all of that. You remove all the previous session. I'm going to start again here by choosing the first variable, the X variable, and basically choose the Y here. And now I have cross-validation, and here it gives you the number of cross-validation folds. Here it chooses as default as 5 folds. If you increase it, should be fine also, okay? So basically, it's a good thing if you do that, okay? But actually, let's keep it at 5 so that we can basically at least get the results quickly, okay? So I'm gonna do that now, start session. So now I'm going to choose also quick, all quick to selection of classifier, okay? This is actually a very good thing. Basically, you have so many of them, but actually you can also have all or all linear, because actually these also, all different types of classifiers will have linear versions that compute a little bit faster. So I'm just gonna choose the same one that we did before, and I'm going to start the training again. Now it's going to do it right away because actually it already opened the parallel pool. Here the results came out as 93%. The highest results came out as 93%. This is actually a much more reliable result than the other one that we got from the no validation. Because the no validation, it so happened that the order of the cases was such that it allowed you to get this high result. But actually this one is much more reliable because it's a combination of results that came out higher and came out lower, basically, and so it's likely for this to be the practical accuracy you would expect to have in the field. Okay, so basically, if you look at that now, let's just look at the 93%. The confusion matrix actually looks good because actually here 6, this is the false negative 6, the false positive is 3, which is actually they should give actually very good results. The ROC curve here is 0.98, which is actually good. This is very good. It's actually very close to whatever you have here. The highest point here, the best point here, would give you 0.09 and 0.95. 0.95, basically, this is the Y, this is the X, and this is the Y. This is the X, which is 1 minus false positive rate is 1 minus specificity. So basically, if I have 1 minus specificity is equal to 0.09, this means that the specificity is what? How much is the specificity here for this point? 91%, 0.91. Because basically this 0.09 is 1 minus specificity. Let's go back, remember. This here is 1 minus specificity. So if 1 minus specificity is equal to 0.09, this means that the specificity is 0.91. So the specificity is 0.91. The sensitivity is a little bit higher. It's 0.95. This is excellent. This actually is excellent. So now we have basically these results are just a subset of all the classifiers. Let's look at one by one. Basically, we can just try, if I see that the KNN is probably performing well, so basically I can go here and say all KNN and run it. Basically, whenever you have something here, it's written as draft. Whenever I'm standing here, I can see here train becomes active. So I just run it here. So basically, it came out exactly the same. Okay, so basically it's 93%, which is okay. Let's try another. Maybe I can try optimizable KNN. Let's see if it gets any better. Now it's optimizing now. It's trying to optimize the parameters one by one. And basically this here will draw the error, the minimum classification error, and the error itself. And basically you will see here that for different selections, the curve will be actually going up and down, but actually the minimum is still here now. Let's see after this optimization how much, basically it's going through all the options now, okay? It's not going to take much longer, actually. Don't worry about that. But actually, if you want to get something optimized, you actually need to have some optimization done, and you have to spend some time to do that. So now, after the optimization, you squeeze a little bit more out of the KNN classifier. You got now 94.5% accuracy. And so now we're talking about, see, we didn't really spend that much time doing classification, doing feature extraction and feature selection, but see here now, we have an accuracy of 94%, 94.5%. It's extremely good, actually, that we got something like that. And basically, the advantage of that here, you can actually also look at the confusion matrix. See here, you have the confusion matrix here. You can compute it from these numbers. You don't really have to, basically, confusion matrix, you can compute it yourself by, I'm going to show you how to do that now, but actually, you can simply just compute the numbers yourself. It doesn't really need that much effort. The ROC curve seems very good also. 0.08 now, so it's the specificity now is 92% or 0.92. The sensitivity is 0.97. It's a little bit higher than the 0.95 that we had before. So this is extremely good. We can do that for all kinds of classifiers. Basically, you can just do that for the support vector machines, for example. Let's try that. Might take a little bit longer for the support vector machine, but actually, we were able to get 94.5% for the support vector machine with cubic support. Basic cubic means that the model is a third order model. Remember the model for the classifier, the model for the curve that you're going to use for your classification surface. You make it as a parametric surface, like a polynomial. So cubic means that you have a third order polynomial. If you optimize that, you're probably going to get a little bit more out of that. So basically now you know how to do these things. Basically, you can go over each one of them. You can go over all of them. You can go over one by one and optimize. You can basically look at the performance matrix from here, from the confusion matrix, from the ROC curve, or whatever. The very nice thing about this app is that basically if I want to get the ROC curve from here, I can basically say that export plot to figure. I got it here as a figure. Basically all I have to do, I can save it now, save as. Basically I can basically save it as, for example, JPG. Okay, Fig 1. And basically, these are the kind of things that I expect you to have in your report, in the report that you're going to submit for the research problem 2. Okay. By the way, I'm going to post an assignment for research problem 2 that includes all the questions that I want you to do, including things like that. So basically, I expect you to use this kind of app and basically get the results out of it. Okay. The nice thing about this also is that you can generate a function for this particular, if this is basically my best classifier, for example, I can generate a function that generates this classifier, generate the model for this classifier. I told you before from the help that we generate a model and then use predict to basically predict the data from this model. Predict or basically get the results for the testing data. You basically using this generate function, basically it generated a function that would give you the trained classifier. This is a model, and it would give you also the validation accuracy. The accuracy that you saw here, the figure that you saw here is going to give it to you as well. Okay, so that you can use the model to classify anything after that. So basically, if you want to train your model, or basically get the model that had the best accuracy to use later on for your CAD system, you can just get it from this function right there. Another way of doing this is if you want to do it right now on your workspace, you can just export the model. If you export the model, basically it tells you which variable you want the model to be in. So basically, it basically has a default of trained model. So let's just call trained model 1. If I say OK, now my model will be basically right there. It's already there. I gave you here some indications that it was exported from the classification learner. It tells you how to classify a certain set of observations. So basically, it tells you y fit is equal to this. So basically, I can just use it like this. And instead of x here, I'm going to put x train just to see what happens. Okay. So basically, it gave me the classification results for the x train. Okay. If I have x test, if I have another set of observations for the testing data, I can just put it there and get the results right away. Okay. So this is extremely nice also. If you're sitting on your computer and trying to get just the model, okay, you can just do it this way. Okay. So what we're going to do now is we're going to basically right now we use only the test data here, the training data here. We're going to generate the features for the testing data, and then use the testing data to basically use it with this model and see basically how the results would be out. Okay? You understand what we're doing? Anything difficult in what I'm saying?
No, it's clear.
Okay. Basically, if you do that, if you understand what we are doing here, if you know how to use the classification learner app, it's going to be much easier for you. Basically, if you want to do research in this area, it's going to help you a lot to do that. So basically, if you know that, you just prepare your data and use it right away with the classification learner. Let me try an example with you that might be interesting. We said that we're going to basically we move the classification problem from the original signal space to the feature space, right? This is what we did, right? So basically, I want to try two things actually. Basically, I'm going to go back here. Remember the part where we removed the feature that were not useful? What I'm going to do now is I'm going to remove that. So basically, I'm going to keep the features that that are not useful. Let's see how the results will become. So let's remember that the best results we got was like 94.5%. Okay. So basically, I'm going to try now and run this. And when I do that, the X train and Y train will now have the 5 features that were not useful. Let's see if they will affect the results or not. Okay, so now X train is 128 by 39. Okay, not 34 because the 5 features were added. So I'm going here and basically I'm repeating these things so that you can learn them. Basically, I'm going to have a new session from workspace. Yes, I'm going to delete that. The previous session will be deleted. I'm going to choose X train. And then I'm going to have the responses from the workspace, which are a Y train. I'm going to keep the cross validation because we know that the no validation is not very good. So I'm going to start session. Let's try the first one here, a quick all quick. Okay, one of them gave us actually better results, actually, which is kind of surprising, but it's not like basically if you see the other ones here, they are a little bit lower. Okay, so basically sometimes if you add the other features, it might give you something that wasn't there before, but actually let's see this one here. What's the ROC curve? Here it's about 94% and 97%, which is actually it's not bad. Okay, usually you get results that are not good. They are not. This is probably like a fluke. This is not something that you would expect to see actually. Basically, sometimes if you let's just keep it like that. No problem. The other thing I want to try, so basically you have to compare the results with the features and without the features. If you're going to do the one of the sequential forward search or the sequential backward search that we talked about, you look at it here actually. You see the performance of different combinations basically by looking at the results right there. Let me try something else. How about if we take the data as is? Okay. So basically, I'm going to have NSigLearn. NSigLearn has all the signals as they are. So basically here, I'm going to, instead of having the features, let's just return that, doesn't matter. I'm going to have X train. X train equals to basically NSigLearn and ASigLearn. Okay, so I'm just going to use the whole data without extraction any feature. Basically, I'm going to have 128 times 1080. I'm just going to use the signals as they are. I'm just going to use the signal points as features. Okay, and see whether it will work or not. Maybe it will justify whether it makes sense to actually have feature extraction or not. So let's try that. So just a change here. X train, X test, Y train should be exactly the same because the first 64 signals represent normal and the other ones represent abnormal. So basically it should be the same. Now I'm going to choose now X train. See now it's 128 times 1080. And I'm going to have the responses from the workspace. See now it's a little bit slower, okay? So because actually the number of points here will make the classification a little bit slower to do. So now I'm going to have also the all quick and see. See now it's kind of slower now. See now the accuracy is here, 68%. 67%, 50%. So now see here, the best result is 68.8%. So this actually confirms that if we use the signal as is without extraction of features, then basically we're going to end up with really poor classification results. Okay, so it's very important to choose, or basically to first of all extract features that make sense and use them instead of the actual or the instead of the signal itself. So the moving the classification in the signal space is usually not useful because of the shifts, because of the different kinds of things that would happen between different patients or for the same patient a long time. And basically, it's better to move the classification into the feature space. You first of all get much better classification results. You actually can train your classifiers much faster because your space is much smaller. Okay, and instead of having 34 dimensions, you have now 1080 dimensions, 1080 dimensions. So basically, the classification will take much longer, and usually when it does that, it usually takes it provides results that are not as good. Second of all, okay, is that clear? Okay, so basically, let me write it down. Go ahead. If you have any question, go ahead.
No, it's okay.
Okay, so basically, let me write these experiments. Okay, there's another experiment, something called dimensionality reduction. Right now, after selection, we have 34 features. Okay, 34 dimensions is really, really large space. I mean, imagine that you have third dimension, basically the physical dimensions are 3, basically. If I have 34 dimensions, this means that I will likely need much more data to be able to describe the variations along these 34 directions. Okay, so it's better to have a little bit less. Okay, how can we make them less? First of all, we have to explore redundancy, or basically remove redundancy. Meaning that if I have a vector, if I have, for example, a feature that was like alpha, and another feature was like 1.1 alpha, these are the same. I don't need both of them. I can just remove one of them. One of the very effective ways of removing redundancies is called principal component analysis. You heard about that in the seminar probably this week. Basically, it takes these dimensions, takes your dimensions, and tries to summarize them. Okay, the summarization of dimensions is based on something called variance, or basically, let's just remove, I don't want to give terminologies that might be confusing to you. Basically, this summary, you basically measure closeness to original. okay? And basically choose the summary that would basically, for example, give you 90% of the information of the original, for example, okay? Or 95% of the original, okay? And see whether that would be a better way or not. There is a way to do that, actually. Let's go back first of all and generate the same exact data that we should have. I'm just going to comment out that. The one that uses everything. I'm just going to write in signal space. Okay, so now we're going to have the usual data that we used to have with the feature reduction and everything. Okay, so now I'm going to go back to the app and start another session. Whenever you change the data, you have to start another session. Also, I'm going to have here X train. Now it's back to the dimension that we used to have, 128 times 34. And from workspace here, it's X train. We're just going to keep the cross validation there as default. Here, there is PCA there. Okay. First of all, we can just choose that. It's fine. For the PCA, we can choose that enable PCA. Okay. And explained variance is basically it's just a measure of closeness. Okay. How close that is to the original. So now it's 95%. Okay. 95% means that it's going to summarize or use a percentage of the dimensions that you have that basically meets the closeness of 95% to the original. Okay, let's try that. Okay. Just gonna, every time you have to say train so that it gets training going. Actually, now it didn't work. It appears that it's not a good idea to do that. Now the best here is 82%. So this means that the closeness of 95% might not be enough. So I'm just going to increase it. 99%. Okay. But actually, it did that for the draft, or it did that for the tree only. So I don't want to have that. The other ones here, the PCA here actually it kept three components. Three components. It basically changed the dimensions from 34 to 3, which is really a big reduction. So basically, I'm just gonna start another. Instead of doing that, I'm just gonna choose all, and then for that particular one, I'm going to change that here to 99%. Yes. And I'm going to start the train. Now it's giving us a little bit better results. So for the 91.4%, now it's we're using 6 components. So the dimensions are 6. The point is with KNN, it doesn't really make sense to have any reduction because basically using the same data. So basically you're changing or introducing error to your data. If it's 1%, even, it's not a good idea. But the other ones might give you much better results. So the SVM might give you some better results. But now here we see that if we don't use the KNN, if you don't use the PCA, it might be better actually. So basically, I'm going to go back and choose that and forget about the PCA. Sometimes it gives you better results, sometimes it doesn't. So you have to try it also. One of the things that you have to try and make sure that whether it's doing basically giving us good results or not. Now it's better results. Now it's 94.5%. Let's try the SVM. SVM or maybe one of the other tree-based might actually see some better results. So maybe I'll just use all SVM and without the PCA. Now it doesn't have PCA. Let's see how good we can get results from the support vector machines. (95.3%). Okay. Okay. Let's try again. The all SVM and basically change the PCA to 99% here. If we can just have it as 95% even. Let's see. No, it didn't give good results. So maybe I can go back and maybe I should try. Maybe for this particular data, actually, it might not give good results, but for other data, it might actually give good results. The very important point that I would like you to basically understand is that each data set has different characteristics. So you have to try different things. All the things that we talked about today is just choosing different classifiers, just choosing different parameters for the classifier, optimizing the parameters of different classifiers. So for example, if I came here and choose the optimizable SVM and choose PCA as none and run that, it's going to optimize the SVM and it's going to give you probably better results, at least as good results as the one without optimization. So it's you know, after you do this optimization, you have a confidence in your model that it would be at least as good as any other model that you can generate using this technique. Okay, so this is a very convenient way of generating results for any classification problem. So if you have EEG data, if you have heart sounds, if you have any type of data, you can basically do exactly what we're doing here. Do some feature extraction, and then take your data and go and use it with this app, this classification learner, so that you can get the best classification that you can get. So your problem now is how to extract features that are useful from your data. If you have features that are not useful, then you'll have a problem. Okay, so in order for me to show you that, basically what I'm going to do is I'm going to go back here, and instead of removing the features that are not useful, I'm going to do the opposite. I'm going to remove all the features that are useful. Okay. And see whether that will affect us or not. Let's see the results first of all. Now we got to 96.1%. This is an improvement. See, we had 95.3% before. Now we have 96.1%. So see, optimization of parameters will actually get you that. If you want to do that manually, it's going to be really difficult. It's going to be really time consuming to do that. So it's much easier to do it here. So basically what I'm going to ask you in the assignment is basically do exactly what we're doing right here. Okay, so I'm going to ask you for parameters for example, one of these particular, or at least two of these, basically, and ask you to optimize them with different conditions, okay? And basically ask you to get the results with a different percentage of PCA, for example, okay? And ask you to give me the ROC curve for whatever results that you present, same things of that sort, okay? So let's now run the one here so that we can get the basically just this is experiment 3 here. Experiment 4. Use features that are not useful. Use only features that are not useful, okay, and see what happens. So if you do that, just gonna run the same code. After we run this code, basically the remaining feature here, we're going to remove the features that have p-values less than 0.05. So we're gonna end up with only 5 features. See here, 128 times 5. So I'm gonna start here from a new session. X train, Y train, same exact parameters, start session. I'm not gonna use that. I'm gonna try quick. Okay, let's try. See now the results, 50%, 72%. Very poor classification results. Okay, so basically, even if we optimize, maybe you can just use one of these and optimize, just use this tree. So that decision tree, optimizable tree. Okay, let's try the optimizable tree and see if we can get any better than that. So the best results are 75.8%, okay, which is extremely poor, okay. So definitely the features that are not significant will not give you performance, or will give you good performance, okay. So this is important to keep in mind, okay. So do you understand now how to do things? Basically, we had the feature extraction here, we had the feature selection here, and we had the classification done after we put the data in the right format using this app. This is basically our first arrhythmia detection system, because basically now we can use this system to classify between normal and abnormal. And we can go back to this data. If you remember last time, we put here the abnormality type 2, for example, 3 was here. I can actually change that to 2 and see the results for the 2. So basically now we're doing binary classification between normal and one type of abnormal. This is actually what we usually do, okay? What we can do is probably do, for each one of the abnormalities, you can get the results or the sensitivity, the performance metrics, the ROC curve, and basically consider it as a different problem generally, okay, different binary classification problem. You understand what we did here? Do you have any questions? So the remaining parts of this course now will be basically, let's have it another page. We have to actually compute the features for the test cases. It's basically going to be exactly the same way we did it for the training case, no difference at all, exactly the same. And basically we're going to compute the features and also select the same ones using the same ones selected by the training. You have to keep in mind one very important thing, very important. Test data is used only for testing. It's not used for selection. It's not used for optimization. Okay, so basically the selection was based on the separation of the normal and abnormal based on the training features. Okay, we're going to use exactly the same features selected by training, and basically remove the ones that were not useful in the training phase, you know, in the testing, because basically we have to have the feature space will have to be the same for the training and testing. You cannot have a feature space for the training data having a dimension of 30 and a feature space for the testing have a dimension of 40. Doesn't make sense. You have to train for the same dimensionality of the classifier. Okay, so basically we're going to do that. You have the option of, we can actually take a break now for 15 minutes to pray Maghrib and come back and do this, or we can do it next time after, basically after you get a little bit of training on the system and basically get started with the classifier learner, classification learner app, so that you can have more questions. Which would you prefer? You prefer to continue today or wait until next time?
I prefer to wait until next time so we can try with ourselves and ask you some questions.
Wait till next time?
Yeah, next time.
Okay, that's fine. By next time, hopefully within the next couple of days, I'm going to post the assignment that you should submit for research problem 2. So basically it's going to be like the assignments I posted for research problem 1. Please go ahead and read the assignment and consider whether you have any problems or basically whether anything that was asked in the assignment that was unclear or you need some more explanation for it. We can do that inshallah next time and the one time after. Okay? We have 2 lectures, we have 2 remaining sessions this term, okay, because we have to finish, basically formally we have to finish on the 26th, but actually our lecture is basically, the lecture of Fridays belongs to the week before. So we have a lecture, the last lecture will be on the 27th, inshallah, okay? Don't worry about the, we're going to have what's called a final exam. The final exam will be basically a take-home exam. It's not going to be, basically just going to be a set of questions, MCQ questions, that are based on the concept that we have in the course, okay? And they are going to be very straightforward. Basically, I'm going to have only 10 marks, something like that, 10 marks for the final exam, and the remaining will be on the assignment related to this research problem, okay? Inshallah, after you read the assignment, we can talk about whether you have any issues or you need to have any support. I'm going to be available after the lectures. If you have any questions, I can have a session, a Zoom session with you and discuss any problems you have, okay? It's very important that the code that we have today here, I'm going to return it to the original version here. Just make sure that it's the original version, basically. I just uncomment. Just to make sure of that, I'm going to run it and basically try the classification again so that we know that it was working, so that when you try it, you don't have any problems. X-train, Y train, and that's it. I'm going to try here quick. We have now 93% and 93.8%. This is without optimization. And if you optimize the KNN or the CSVM or the trees or whatever, you're going to likely get more than that. So basically, this is the code that will generate the data that you can use directly and go ahead and use the classification learner based on that. If you have any questions on how to use the classification learner, please don't wait until next week. please contact me by email or WhatsApp or basically any means you want, and basically ask me the question, ask you out any problem you have with the app. Okay. Any questions? The last thing actually we're going to do for next time is just compute the performance matrix. Basically, you're going to get the model from the app, the classification learner app, and from the model we're going to get the results, and from it we're going to compute the metrics. Okay. So if you don't have any questions, inshallah, we'll see you next time, inshallah. Okay.
Okay, Doctor.
شكرا. السلام عليكم.
وعليكم السلام ورحمة الله.